Hello everyone. Today we'll discuss association rule mining. It is also known as market basket analysis because of its origin. However, it's not confined to markets. Let us first try to understand the context in which it originated. Many of you might have heard the classic story of bears and diapers. So some supermarkets realized after the study of many transactions that people who buy diapers were actually quite likely to buy beers also. Initially, it was a bit surprising because, these are not the things that you would expect people to buy together. However, later they realized that most of the, later they realized that many a times males in the family would go for diaper shopping over the weekend and then they wouldn't like to make multiple trips. So along with diaper shopping, they would do beer shopping also. And in fact, they decided to make use of this knowledge and they stacked the things together. And it resulted in increase in sales of both beers as well as diapers because things were easy to locate. So from there, people started thinking, are there any further such associations? Because if you find something which is useful to you, you are more likely to buy it, right? So that's why I started the concept of market basket analysis. So it mainly works on transaction type of data. So what do I mean by transaction data? Suppose you have different objects that are sold at a particular shop. So you have say O1, O2 up to OP. P can be very large. It may be like in thousands or something like that. And you have different transactions. Transaction 1, transaction 2, transaction N. And this N is also going to be large because N is number of transactions. Okay, so that is also going to be very large. And you can have two types of data sets. You can either have a binary data. So binary data means what? If a particular transaction involves purchase of a particular object, you put 1. If it doesn't involve purchase of that object, you put 0. So that is one sort of transaction data, that is binary data. Another can be the quantity. So if a particular transaction involves purchase of say 5 items of this particular type, then you put 5 here. But mainly binary transaction data is more used. Now you might have realized that this is a huge matrix and it's going to be a very sparse matrix because most of the transactions would have very few items from among the items available in that store. Hence, every row is going to have many zeros, much more zeros than ones. Okay, so this is a very sparse matrix. Hence, dealing with it is slightly difficult. Now, why do you want to analyze such transaction level data? So as I said, one of the aims is to create favorable sales strategies. Okay. There may be many other reasons also. For example, you may want to give special coupons to some customers. So you want to decide which type of coupons should be offered to which customers so that it leads to higher sales. In fact, generally in such market analysis, characteristics of a customer are measured in terms of 3 parameters. Those 3 parameters are frequency, recency and value. What are these? So if suppose I am considering data for the past year, frequency would compute how many times a particular customer has visited that store. Okay, so number of visits. Recency would mean duration from the latest visit. Duration from the latest visit. And value would mean average amount of money spent over entire year or even total. It doesn't have to be average. You can say total amount of money spent by that customer in the store. Now, frequency of course should be high if for a good customer, value should be high, whereas recency should be low if you are measuring it in terms of duration from the last visit. So it should be low, means the visit should be frequent. Now, some of you might be thinking, how do you know, do you really keep track of whether each customer has visited so many times? You have to remember, nowadays with digital register, things are pretty easy. And in many of the stores, they ask you for your registered mobile number so that they can give you some store credit, some extra points, etc. So with your mobile number, it's very easy for them to keep track of whatever you are purchasing. Okay. In fact, Kaggle does have some data sets of this type. One of the students did some project in the past on these types of data sets, and they were like huge data sets. There were many files. Handling those files, Excel was unable to open those files. And the person had to write shell scripts and get data for each customer from multiple files, because for every month I think there was one file and there was some customer ID type of column. So then from each file he extracted data for each customer and then combined few features, added few features, and finally got like one row for every customer, something like that. So handling such data becomes very difficult. But still, of course, if data is there, you would like to analyze it. In fact, even your recommender systems on Amazon or Netflix would follow something similar. So when you purchase things on, say, Amazon or Flipkart, you might have seen "you may like this." So how do they realize what you may like? Because they are trying to study your pattern, and they have huge amount of data with them. Okay. So for dealing with such types of things, this market basket analysis or association rule mining was used. But remember, this is not the only field where it can be used. Wherever you have some sort of binary data, or you have data which can be converted into binary things and you would like to see associations, this can be used. In fact, one of the project groups had used it for relating symptoms of respiratory disorders, symptoms of various respiratory disorders, which symptoms tend to occur together, or which symptoms are more associated with a particular disease. So such types of studies can also be done via the same techniques that are used in market basket analysis. Hence, I prefer the name association rule mining rather than market basket analysis, because we don't want to restrict the techniques to just the transaction data. Okay. Now, what do I mean by associations? So, the terminology that now we will use would be from market basket. So, for example, bread implies butter can be one association. What do I mean by bread implies butter? A person who has purchased bread is quite likely to purchase butter also. Okay. Or maybe bread implies jam. This can be another association. Person who has purchased bread is quite likely to purchase jam also. And now you would like to see which of these two associations is stronger. Okay. So these types of studies can be done, and in fact you can draw like networks where one thing implies other, another implies third, and so on. Okay. So let me first introduce the terms that are used. One commonly used term is item set. What is item set? Item set is collection of items. Now it can be singletons as well as doubletons, tripletons, anything. Okay. So singleton bread can be one item set. Another item set can be, say, bread comma butter. Okay. So such subsets of your total collection of objects are known as item sets. Okay. Then we define something called as support of an item set. What is support of an item set? Support of an item set is number of transactions containing that item set. So number of transactions containing I divided by total number of transactions. Okay, so if you have, say, 10 transactions, out of which, say, 5 people have purchased bread, then support for bread would become 5 by 10, that is half. Now, as you might have realized, support is kind of like probability. Okay, if you assume everything to be equally likely, then support is like probability, and hence support is always going to be between 0 and 1. For every item set, support would be between 0 and 1. So let me take some sample transaction data so that we can illustrate support and other terms that we are going to study. So suppose we have butter, then let's start with bread, butter, milk, and suppose apple. Okay, and I have transaction 1, transaction 2, transaction 3, 4, 5. Okay, 5 transactions. Suppose first person has purchased bread, butter, but no milk and apple. Then suppose I have 1 0 1 0, so bread and milk but no butter and apple. Then 1 1 1 0. Then suppose 0 0 0 1 and maybe 0 0 1 0. Okay, so suppose these are some 5 transactions. I have arbitrarily put numbers, there is nothing special about them. So now support of bread you can see would become 3 by 5, support of apple would become 1 by 5, and so on. Okay, so support for apple would become 1 by 5. Now we don't want to stop just at support, we want to form rules. Does purchase of one object increase the chances of purchase of other object, right? So for such rule we are going to define something known as antecedent and consequent. So everything on the left would be termed as antecedent and everything on the right would be termed as consequent. So antecedent implies consequent. Those are the types of rules that we are going to form. So a person who buys bread is highly likely to buy butter. If we want to frame a rule like that, then bread becomes antecedent and butter becomes consequent. Okay. Now what are the parameters which can measure strength of such rules? Because you don't want to, technically you can form every pair, but you would like to see which pair is more sensible. And one more thing, neither antecedent nor consequent have to be singletons. You can have doubletons, tripletons. So you can have say bread butter on left side and then milk on other side, or say bread butter jam on left side and milk on other side. So that is also allowed. Antecedents as well as consequents can be sets of cardinality more than one. Okay. Now what are the parameters that can be used to check the strength of these rules, whether these rules are actually rules or not, or are they just coincidences? So one important parameter is confidence. Confidence of a rule I1 implies I2, where I1 I2 are item sets, is defined as conditional probability of purchase of I2, conditional probability of purchase of I2 given purchase of I1. Okay, so what is the probability that a person who has already purchased I1 is now also going to purchase I2? Okay, so technically it is probability of purchase of I1 and I2 both upon probability of purchase of I1. Correct? I am just writing the definition of conditional probability. In terms of item set, if I want to write, then I1, I2 both means the transaction should have items from both I1 and I2. So number of transactions containing I1 and I2. So I1 union I2. Number of transactions containing I1 union I2 divided by number of transactions containing I1. Now you might have started thinking that in conditional probability we have intersection in the numerator. It is actually intersection, I1 and I2 both, but when I want to write in terms of transactions, I have to write union, because if say I want to say bread and butter, my transaction set should be union of bread as well as butter. Okay, so this union intersection business might be slightly confusing, but do note that it is not contradicting each other. Okay, so how do I compute this? Number of transactions, I can also write this in terms of support of I1 union I2 divided by support of I1. How do I get this? I can divide numerator and denominator both here by total number of transactions. So numerator becomes support of I1 union I2 and denominator becomes support of I1. Okay. Of course, since this is conditional probability, it is again going to be between 0 and 1. So confidence of any rule is going to be between 0 and 1, and confidence near 1 indicates the rule is good, rule is strong. Okay. So higher the confidence, higher would be the strength of the rule. Okay. But this confidence does have some limitations. So let us take one example. Suppose I am asking people whether they drink tea or coffee. So I have tea here, coffee here, and then tea here, coffee here. Why? Because we also want to see people who drink both. So 90 people drink only tea. There are 5 people who drink tea as well as coffee, and there are 5 people who drink only coffee. Okay. So now, so this is 5 would mean here also I can write 5 in case I want to form a rule of the type coffee implies tea or tea implies coffee. So these are basically same people, they are not different people. These 90 are purely tea people, these 5 are purely coffee people, and so total we have 100 people. Okay, out of which 90 are purely tea, 5 are purely for coffee, and 5 are drinking both tea as well as coffee. Now if I want to try confidence for rule of the type coffee implies tea. Okay, so a person who drinks coffee is also likely to drink tea. It would be number of people drinking both divided by coffee. Divided by coffee means how many people are there? 10 people who drink coffee. 5 purely coffee and 5 both. So this becomes 0.5. And similarly, confidence of tea to coffee becomes 5 divided by 95. So this is very close to 0.05. Okay, because 5 by 100, close to 5 by 100. Now, technically we know that both these rules make no sense. If you drink coffee, it doesn't make you more likely to drink tea. Okay. Similarly, if you drink tea, then it doesn't make you more or less likely to drink coffee. Okay. Even though the intersection has 5 people, somehow we get a feeling after looking at this number that coffee implies tea has quite good probability. Okay. However, that is happening because support of coffee is very low. Because support of coffee is already very low, this 5 is also making a huge difference. Okay. Hence, some people don't like confidence measure because it is affected a lot by the support of the antecedent. Okay. So, what is an alternative? Then people came up with something called as lift. So, lift is scaling confidence. So, lift is confidence upon expected confidence. Now, what do we mean by expected confidence? So, expected confidence is confidence which is expected under H0 kind of thing. Under H0 means like no association kind of thing. So, if there is no association, then we know that probability of intersection is probability of product of the probabilities. No association means independence. Okay. So, lift is written as probability of A intersection B upon probability of A into probability of B type of thing. So, here you are actually having support of both A and B in the denominator. So, it is going to reduce the effect of support. Okay. But the problem is, okay, how do you interpret lift? Now here lift doesn't have to be less than 1. Lift can be less than 1, greater than 1, equal to 1, anything. So lift equal to 1 means no association. So the rule is useless because it is as good as independence, right? Whereas lift greater than 1 would mean positive association because the probability is more than expected under independence, and lift less than 1, of course it has to be significantly different than 1, then it would mean negative association. Okay, but lift takes care of the support issue that we discussed for confidence. However, lift is also not like completely fault free measure. The problem is, from the formula you can see lift is a symmetric measure. Symmetric in the sense, it doesn't matter whether you are computing lift of the rule of the type A implies B or rule of the type B implies A. You are getting exactly same thing. So, if you want to make a policy decision, lift may not be of that use. Okay, because you don't know who is causing increase of sales of other thing. Okay, so symmetry of lift can become disadvantage for some people. Now, so people keep on searching for newer and newer measures. One such measure is leverage. So what is leverage? Leverage of a rule A implies B is support of A union B, means probability of A intersection B type of thing, minus support of A into support of B. Okay. Now because we are having an additive type of structure, negative, leverage can be negative, positive, 0, anything. So if leverage is equal to 0, then again no association, because it is kind of probability of A intersection B equal to probability of A into probability of B type situation. So leverage equal to 0 means no association. Leverage greater than 0 would mean positive association, and leverage less than 0 would mean negative association. Okay, so leverage is another measure that people compute. Then there is something called as conviction. Okay, so what is a conviction? Conviction for the rule A implies B is defined as 1 minus support of B divided by 1 minus confidence of A implies B. Okay, if you want to write in terms of probabilities, it would be probability of A into 1 minus probability of B divided by probability of A minus probability of A intersection B. Okay, so you can see here, if I simplify, this is probability of A minus probability of A into probability of B divided by probability of A minus probability of A intersection B. So it is again dependent on something similar, but now it is in the reverse terms. Okay, it's in terms of the complements of the sets. Okay, going from here to here is easy. You can work out the proof. You can just substitute the formula for support and confidence and you will get the result in 1 or 2 lines. Okay, so conviction of a rule can also be measured. As you can see here, conviction is again going to be positive always. Can you see that? Numerator is of course positive, and in the denominator also, because A intersection B is subset of A, you will always get a positive number. So conviction cannot be negative, it is always non-negative. So it's always greater than or equal to 0. And if conviction is less than 1, then what happens? And if it is greater than 1, then what happens? If conviction is less than 1, it means probability of A minus probability of A into probability of B is less than probability of A minus probability of A intersection B. Okay, if conviction is less than 1. This means that probability of A into probability of B is greater than probability of A intersection B if I cancel probability of A from both sides and multiply by negative sign. Correct? So this would mean that there is a positive association. So conviction less than 1 would mean positive association. Conviction greater than 1 would mean negative association. Okay. So this support, confidence, lift, leverage, conviction, these are the things which can be computed to measure strength of any given rule. Okay. And association rule mining tries to find such rules from all possible transactions, all the available transactions. Okay. Now you might have realized that finding such rules is not really an easy task. There are like too many objects and hence too many possible rules. So if you try to compute, support or lift for or confidence for every rule, you are going to have too many things. Okay, because from all objects you have to first prepare item sets, and there are no restrictions on item sets like they should be of particular order. They can be singletons, doubletons, tripletons. So there are too many possible item sets and hence too many possible associations. So to reduce this computational burden, people have suggested an algorithm called as Apriori algorithm. Okay, what does Apriori algorithm do? Apriori algorithm tries to reduce at least some of this work. So let me write down the algorithm. The first what we have to do is we have to compute support for every singleton item set. Compute support for every singleton item set and decide some threshold. Okay. So actually threshold should ideally be decided in the beginning. Decide some threshold. So at the next step, consider only those singleton item sets. Consider only those singleton item sets whose support is greater than the threshold. Whose support is greater than the threshold. Why? Because if the support is less than threshold, then they are not present in most of the transactions. So you may not get much useful information out of them. Now consider doubletons. Which doubletons you are going to consider? Not all. So consider doubletons who are not supersets of ignored singletons. What do I mean by ignored singletons? Those whose support was less. Okay, let me explain with an example. We can go to the transaction data that we are considering. So yes, so here you can see support of Apple is 1/5. So if my threshold is suppose 30%, then Apple is not going to be included in my analysis, and because Apple is not there, including bread apple, butter apple, milk apple also doesn't make sense, because support for bread apple is going to be further less. Am I right? Support for bread apple means it's kind of like probability of intersection of bread and apple. So of course it is going to be less than probability of apple. So if we drop apple because it has support less than the threshold, then we have to drop every doubleton involving apple. So bread apple is also dropped, then butter apple is also dropped, and milk apple is also dropped. Okay, so we have to retain only those doubletons which are not supersets of the ignored singletons. Got it? Then you compute support for all those doubletons. Okay, so compute support for these doubletons. Now again discard those which have support less than the threshold. So discard those doubletons which have support less than the threshold. Okay. You repeat this procedure for tripletons, but again we have to consider only those tripletons which are not supersets of the discarded doubletons. Okay, so now consider only those tripletons which are not supersets of the discarded doubletons. This way you go on doing this till we reach the final size. And now here with only these item sets we try to form the rules and try to check strength of those rules and then locate the rules which have very high lift or very high confidence or very high leverage, etc. Okay. And all these things can be actually represented via network type of graphs where you can indicate strength of an edge by confidence or support of that, not support, confidence or lift or leverage of that association. Okay. So this is all about association rule mining. Let me stop here. Thank you.